So yeah, good. Rust, unsafe. Yeah, does it work? 111. Can you hear me? Perfect. It's a Zoom moment. So yeah, excited to hear you and see you in this room. So in the first talk today, I will speak a bit about parallel programming in Rust, how to achieve blazing speed, and a bit about myself. My name is Evgenii. The last name is unpronounceable, and I'm a senior software engineer in Bloomberg. And I should say in advance, I don't represent all the opinions of my employer, employee. I'm an employer, but it's only about my personal experience. In Bloomberg, we love C++ a lot, and we also love Rust, but I will speak only for myself. And for the life, I write mostly C++, Rust, bit of Python, bit of Erlang, Haskell a little, yeah. And I usually work on high-performance systems and infrastructure tools, and usually our work, as you know, is about how to move JSONs in fancy and highly performant manner. And I got a PhD in researched academical stuff about parallel computing system, compilers, and GPUs. So it seems like I'm excited about parallel systems and how to make things blazingly fast. Yeah. So let's move. We will speak a bit about how to improve performance, how to make the difference between concurrent, parallel, and asynchronous computing, and what are the high-level parallelism approaches, low-level parallelism stuff. We'll speak a lot about unsafe, and something about the future of GPUs. So yeah, about parallel. So yeah, let's make a really small case study. Let's go with UV. Yeah, you know, UV is modern alternative for PEEP, for poetry, and we initialize our project. We add polars. It's a data frame library ported from pandas to Rust, and we get rough. It's a static checker like pylint, and we run the program. We're trying to get all the crates IO dump with data from about all the existing crates, and we're trying to understand how blazingly fast it is. So can you see where I'm moving? So yeah, we're trying to run it, and guess how many blazingly fast crates do we have? 100%? No, not bad actually. It's humble and worth to be proud of. So turns out a lot of tools we use on daily manner in our work with different projects are actually written in Rust. Yeah, so it's UV, polars, rough, FD if we are for the shell, and also cat is rustified recently with bad cat. And I guess you're running in that, your favorite editor or whatever, and run it in WAB terminal. Yeah. And passive kernel, I also read it in Rust. It will be a great talk today with Alice. So yeah, let's understand why do we have this syndrome related in Rust. So first of all, it's only about bragging, yeah? No, not only. It's about how to make our tools faster and performant and safe at the same time. Yeah, so we can achieve more work at the same time. So it's actually about caring about user and about users of our system. That we do more work. Yeah? And let's apply a holistic approach how to extract sources of parallelism on different levels. So first of all, we get from the really low level from hardware. We got instruction pipelines in processor, so it means we can do more work with pipelining stuff, yeah? And we also got superscalar processors from 90s, I think, yeah? And we got vectorized CMD, so we can execute multiple instructions at the same time, yeah? And when we move to the higher level, to the task level in the operating system, we have processes or threads, or if you go with language level primitives, we got green threads in JVM or in Erlang or with Go, so we got task level parallelism here. And at system levels, we can just put an external accelerator just near our system and run it on GPU or on TPU. And of course, we got distributed system on a system level. So it means we can utilize message passing interfaces between different components on the host or even between hosts, yeah? So actually, we can extract parallelism on different levels, yeah? So if you are speaking about difference, yeah? It's a subtle difference, but it's really important between parallelism, concurrency, and asynchronicity. They're actually quite different, yeah? So concurrency is how to actually run multiple tasks using the same processor, yeah? So it's about this, or whether it works. So it's how to make one CPU run multiple tasks at the same time. And it's usually achieved by context switching. So processor just get the thread state, it switches to another one, and we got pseudo-parallelism. And we can achieve the truly parallel execution only if you have multiple CPUs, yeah, multiple cores. So if you speak about CPU, it's core or CPU or, I don't know, socket, it doesn't matter, yeah? So it's the only way to have multiple cores, because the execution will be actually parallel. And sync versus async, it's a little different, yeah? Because synchronous model is how to execute multiple tasks in sequence. It could be different functions in the language or different threads, so we can actually go from one to other, yeah? And with asynchronous model, it's about making stuff interleaved in a different way. So actually, asynchronous versus synchronous is quite different from concurrent and parallel, and we don't need to have a misunderstanding between them. Of course, Tokyo framework can run with multiple threads, so it's a good sign, right? And we will focus about how to achieve parallel program execution model with synchronous model. So it's the topic for today. And for abstractions, we got a ton of them. And if you go from the surface to the bottom of the ocean, we can go from really, really high-level data parallelism from Orion, and from, for example, building your program in release. I hope you don't forget about it. And if you move a bit down, we got primitives to build high-level concurrency. It's thread pools, it's thread affinity, it's understanding about how locks work, and all the concurrency primitives needs to be actually implemented, yeah? We'll dig a bit how to do it. It's about how to build mutex, how to build lock-free stuff, how to make a queue or a channel. And if you go a bit down to the hardware, to the bottom of ocean, with no light at all, we'll get to atomics. Atomic operations at the processor level, and CMD execution, and all the effects of caches, yeah? So it's a bit unsafe in Rust sense, so yeah, we'll see how to do it. And also GPU. It's a bit novel for Rust nowadays, so we'll see what the state of support is, yeah? Usually all the layers are quite isolated from each other, but sometimes we got abstraction leaks. Oh, this works? This doesn't. Oh, sorry. Hardware problem. They are not concurrent. So yeah, they're not isolated well, but Rust developers try to do the best work to make them isolated. And of course, we can compose all of them. We can have message passing in the same way with CMD optimizations, yeah? So let's start with very, very high-level task-based data parallelism. It's Orion, yeah? So it resembles the typical problem with iterators, and the only difference is into par iter, yeah? So the rest of the program is the same. You just change one letter, okay, 4 letters, and you can achieve an improvement, yeah? And the best thing, it's not sequential. It's based on a thread pool. So here goes the magic. It's a library. It's not a built-in functionality in Rust. So it's a most significant difference between how other languages implemented. For example, in C++ 17 is a part of standard. It took only 20 years to get it here. So in Rust, we are a bit more lucky. And in Java, we have streams, we have parallel streams. It's in language, and different languages, they probably lack a few concurrent primitives, so high level. So in Rust, we are quite lucky, yeah? And how does it work? We have a trait called parallel iterator. It kind of mirrors the standard one. And we have a converter from standard operators, from standard iterators, parabridge. And of course, we can construct it with only into par iter method, yeah? And it has plenty of methods, because it's not a iterator trait. Ryan has to implement all of them, and I think we got covered with every case we need, yeah? And for random access, when we know the size of our data set in advance, we can use indexed parallel iterator, yeah? So if you have this, we can pick this particular item. Ryan also offers us a few specialized methods. For example, we can ask for chunks, so we'll go chunk each after other. We can go with a sliding window, and of course we can split, yeah? So for example, for strings, Ryan also allows us to have a parallel string from a normal string. So for example, this example, we'll make the parallel execution for multiple lines, so we can have JSON processing in a really performant way. Yeah. And of course, it's also have sorting, and the main building block of Orion is the thread pool. Yeah. So all the functions we see in this slide, they should be ideally pure. Yeah. So they don't share the state because we can do it with iterators. Otherwise, why do we use them? Otherwise, we need to have a synchronized access with args or mutexes or atomics. And it's not a typical fork join model we can see in the book. It's a little better. Yeah, it's a dynamic balanced scheduler. So it's a work stealing scheduler. It means the data is not pushed to threads. So Orion doesn't say, okay, this thread, get this chunk, get that chunk. We get data flowing to threads. Yeah, so it means each queue has its own, each thread has its own queue. And if the thread, for example, is free from the load, it can grab another thread data and it can start processing it. Yeah? So we have much better performance, no stellar threads, better distribution for uneven loads. It's really useful for us, and it's really great. Orion allows to do it inside. And internally, Orion is data-driven, so we have different models. So for example, usually data flows from the left to the right as we write the code, and all the steps are coordinated with heavy plumbing inside. So if you have to implement some additions, it's quite difficult, but usually it's just enough to see that data is actually flowing to the threads. And the main building block is how to split the data. So you can use this one to make your parallel operator work. Yeah. So join actually do a really simple thing. It runs two things in divide and conquer manner. The first lambda goes to the current thread. The second lambda could go to the different thread or to this particular thread, because we can analyze how much splits do we need based on the data. Yeah. And if you need to make a really specific case for your data, you can hint the Rayon about how your data is organized. And of course, the data should be sent because we need to move data between threads. Yeah. And the thread pool of Rayon is of a predetermined size. So it means global thread pool is created initially because when the thread is created, it's really expensive, and Rayon needs to understand how much CPUs do we have. You can override it with environment variable or with explicit operator, and you can also construct your own thread pool just to make it for a specific part of your program. And how actually we understand how many threads do we have? Here goes the difference between Linux and macOS. I don't even mention the Windows. And actually, we're happy that this concept is abstracted by Rust. We'll see this a lot of times here. Rust tries to make our program really isolated from platform details. So we can ask, how many logical CPUs do we have? Yeah, and it also applies cgroups, so we can understand when we are running in Kubernetes or Docker container, and it also counts, unfortunately, hyperthreading cores, and it's Faux core back in 25, I think. Yeah, it's about how to make threads running on the same core. Yeah. And if you deep dive a little, we can go with an MCPU crate. It allows us to understand how much CPUs do we have, and it can also distinguish between offline and online threads. It could be a difference if you have a really sophisticated ARM processor with offline cores. Unfortunately, NAM CPUs switch to return all the cores at the same time, so it could be a little difference. So if you want to understand it, you need to go back to system calls. Yeah. And for physical processors, it's a bit more difficult. We can ask about how much exactly physical cores or processors do we have. And we should also care about NUMA. Yeah? And NUMA is about having different processors sitting in different sockets. So they're interconnected with interconnects in CPU board. So if you run a really CPU intensive task, you should understand the difference. And the difference is that threads could migrate between cores. It's really good because developers don't actually care about how the headway scaler works. But the bad thing, we can experience cache misses and contention. And for example, let's start with simple code, how to pin a CPU to get CPU affinity. We go to libc, we call the set affinity. So yeah, looks nice, but unfortunately, we need to write unsafe code. So do we need to stay performant or safe? Why not both, yeah? Unsafe doesn't mean your program will immediately become unsafe. It doesn't become C++ code, it doesn't shoot to your feet. So it's actually about the developer who is responsible to ensure the invariance of the type system, yeah? And to interface with system libraries, libc and kernel, you need to have unsafe, yeah? Because all the FFIs, all the interfaces between your program and the system, and especially to hardware, are inherently unsafe. So don't be afraid. And the best advice I can tell is to isolate as much as possible unsafe code, and probably to apply good advice about static verification and static analysis. So we can have all the unsafe specific code really isolated. And if you run that program I specified before for CPU affinity, we'll get this problem on Mac. We need to handle differences between operating systems. And we can do it with a really handy thing. It's a difference from the C and C++ I like the most. We can do it in code. We can understand which platform do we target and which architecture do we target. Yeah, it is a CFG flag passed to our program, and we can utilize it by specifying, okay, this function will run only on Linux, and this function is run only on Mac. Yeah, it means we can combine all the features. We can write a really tailored code for this specific architecture and operating system. And we can also utilize, I'll show it later, a few features. So to understand from the academic level perspective what the parallelism of program are, we need to go to Amdahl law. So the practical outcome, if we have 10% of sequential code in the program, we are doomed because we cannot have more speed up than 10x. Yeah, so we'd like to go to this line, but unfortunately we're here or even here. Yeah. So we have a lot of scalability blockers. First of all, it's critical section, the sequential code. Then we got a synchronization overhead. It's about mutexes being slow. And if you apply message passing, we'll also have some overhead because if you grow with thread count, the overhead for communicating between threads, between tasks, it's really significant, yeah? And the log contention is the thing. If you have only one thread with only one log, it's not a problem, yeah? But since the thread count grows, and we have different threads trying to acquire the same log, it could be a problem. The log contention is a problem. And to understand how to measure it, let's go to perf, yeah? Perf, it's a Linux utility. It's an interface to the kernel, allowing us to understand the performance counters, performance events, and the trace events. So we can go and record some stuff for our program or for CPU, and then we can go to the console and get tons of screens of reports, yeah? So this is why we usually use flame graphs. It's an invention, okay, the Brandon Gregg popularized this thing. So unfortunately, if you want to use it right now, you need to install Perl and run a lot of scripts, because integration for flame graphs with perf is broken in different packages. So that's why people had rewritten it in Rust, yeah? So we get Inferno Create, which allows us to have a flame graph for every program, even on Mac, because on Mac it backs to the gtrace. Gtrace is another framework. So we can have our program profiled with both perf or trace. And we can spot performance blockers. So in this case, I profiled a ripgrep program, and we can understand that this part, for example, it takes much more time than other, yeah? So actually, it just visualizes the execution time, yeah? But unfortunately, the problem is with threads, we cannot see the difference, yeah? Because we can gather all the tracks for each thread, yeah? But we cannot say the performance of the parallel program. For this, we can go with a naive approach. Time exists from 70s. We can go with scientific approach, the hyperfine. It's a really handy statistical benchmark. So if you got a program isolated as a binary, you can run it and get mean, deviations, and all the stuff useful for us. And with the commercial approach, grab until we tune. I don't know, is it available for open source? But yeah, could be a good choice, yeah? And the pragmatic approach is to use criterion RS. It allows us to have almost the same as hyperfine, but inside the program. So you can build benchmarks inside your tests, yeah? So, okay, to actually make our program fast, we should understand different approaches. It's really simple, yeah? We can only go with shared state, or we can go with message passing, yeah? And shared state could be achieved with thread safe data adapted by mutexes and atomics, and let's start with a really simple one. If you need to have a thread safe access to mutable object, it's only arc. Usually we need to modify them, so we go arc with mutex. You all know this, yeah? So it's a really simple example from the book. And we got multiple threads. We got a counter, which is cloned between threads, because clone just increases the reference count. It's really simple, yeah? The downsides of this program and this approach, yeah, that mutexes are really heavy, yeah? So if it's contended, so multiple threads trying to acquire the same mutex, it could go up to tens and hundreds of microseconds, yeah? And it usually calls the kernel. And it means it could be slow, yeah? Modern mutexes and the ROS implementation of SED mutex, it allows us to have a more lightweight alternative because it uses the futex call, so it's easier to use than, I don't know, the pthread mutex. And if you want to have a really advanced mutex implementation with spin locks, and go for parking lot. And if you're trying to have async mutexes, please refer to async. So yeah, the good advice is not to use async mutex probably. So yeah, that's the downsides. For message passing, it's a second alternative. We communicate just by sending messages. So we don't share the state. We don't use the mute. We don't use mutexes at all, yeah? So it's well known in scientific computing and in typical approach with Go, with Crystal, with Erlang, and it's also a foundation for the actor model. So a really simple example from the book as well, I suppose, yeah? It's about how to make one consumer and different producers. So we just push a lot of data from different threads, and we just clone the sender, and then we receive all the data in the receiver, yeah? Pretty simple. But channels go with different flavors. So first of all, we have unbounded queue. It seems it doesn't block. With a bounded queue, it's a different approach. It allows us to have a back pressure, so we can utilize it in our business logic. So we don't need to throw a lot of messages and just allow receiver to go with it. We can use the try methods and timeout methods to get with it. Yeah. So type T usually, no, it's not usually. It must implement the send thread because the data is sent between threads. Yeah. So the internals of this is pretty complicated. So the channel shares the buffer and the registry. So it knows when the sender is trying to send the data to the buffer. When it's done, it notifies the registry, and registry says to the receiver, okay, you can grab this one, yeah? And when the receiver completes with getting the data from the buffer, it notifies the registry again, and it goes to the sender, okay, you can place another item, yeah? Pretty simple, but it requires a lot different things to be implemented in channel. So if you need to have a more advanced stuff, like multi-producer, multiple consumer, you can go with Crossbeam. It's really nice toolbox, a nice crate to have. It's kind of nightly for nightly. So all of these structures are implemented first in Crossbeam, and then they're ported to the standard library. So for example, if you want to have multiple consumers, you can go with this or enable nightly. Yeah, and yeah, why use it? You'll probably have a better performance. You'll have extra stuff like tickers, alarms, and allowing to select. Yeah, and also it's a foundation for Rayon. For deck is a work ceiling deck. You can reuse in your program if you want to have it instead of just a simple fork join. Yeah. And the normal array queue, which you can share between threads without using mutex. It's really handy. Use it. And yeah, it's not a simple mutex inside, because otherwise it will be insanely free. It's a lock-free data structure. So it means we have a buffer with pre-allocated buffers, pre-allocated data slots, and we have atomic indices pointing to head and tail. So all we do, we just move the head, move the tail, and to do it, we need to use atomics. So what is atomic? Atomic is a hardware primitive. It's implemented not in Rust, not in C++, not in library. It's implemented in hardware. Ask the ARM guys. So it's a very, very low level. It's executed only with guarantees it's done or it's not done. Yeah. Unfortunately, it's really limited. It's only a set of basic types, integer types or a single byte. Yeah. So we have a really, really highly platform-dependent code dealing with atomics. So we have load store, we have really simple structures like add sum, subtract sum, and of course we have a foundational structure, compare and exchange. So let's see how Rust implements it. It's stable code, it's fine, yeah? So first we go with flag. We can, the Boolean swap is the second one. Yeah? We can set the flag, we can read the flag. We don't need to protect this with mutex. Also, we can have an operation, more about ordering later, with atomic ints. And finally, it's a structure we talked about before. It's set this value only if the old value is that specific value. Yeah, seems like a really complicated thing, but it is. So the atomic ordering. Why do we have ordering? It's the access semantics because all these operators can be reordered with compiler or even with hardware. So if you want to implement the dependency between of them, you need to go with a release acquire. So you say, okay, this particular variable, this store, like setting the value, it depends on the setting, yeah? So it means we have happens before relationship. If you don't, you can go with any scenario, right? And of course we have sequential. It doesn't use it at all, so yeah, don't use it. Atomic operations are implemented in different ways. So in C it's intrinsic. It's Rust, it's also intrinsic, and if you use the got bolt or the cargo show awesome, it's a really good thing because you cannot put your whole program into got bolt. So we can see the lock instruction, yeah? So we run it for Intel processor. I don't know where is it, yeah, it's for Intel. So it's only about locks prefix. And if you go with ARM, ARM is weakly ordered. So it means we get less guarantees about how does it work. And it means if you go with the high performance, you need to utilize relaxed ordering. But if you go with x86, it's usually, not usually, okay, it's always a strong platform. But the bad point, if you run and test a program on the strong architecture, you can easily crash on weak architecture. So get the weakest machine you can possibly get, weakest in the terms of guarantees, not about the performance, and test with this. And if you're going to onboard the modern RISC-V or port your software to Graviton in AWS, you should use these primitives. Yeah? So the lock-free algorithms are actually based on these atomics, but how about more heavy data structure about our JSONs? Yeah, so we can have a locking primitive over atomic. Yeah, so a very simple example, very simple or no, a simple example how to implement a lock is this. So the core is the lock swap. So we're trying to continuously acquire as a variable, the atomic variable. If we cannot do it, we just yield. So it means we just burn the CPU. We go to the infinite loop. And when we are done, we go with ordering release. Yeah? So we just clean this flag. So we must implement, if it's safe, implement unsafe trace for our mutex. So we say, OK, this is safe, trust me. Yeah? I checked it. So we can use this structure as a normal mutex. But I think you don't need to implement it because we can have a lot of problems. For example, the ABA problem about missing writes, so it could resemble your some problems with SQL, with transactions. So yeah, it's really similar. You can miss some writes. bad thing, yeah? So that's why people try to reuse the implementation. So in this case, go to crossbeam, go to parking lot, and yeah. When you should use it? If you have a lot of threads and you have a lot of logs, you should probably go with log-free data structures. If the log is rarely acquired, so the program is not contented at all, you better use the normal mutex with log-based structures, because it will make the whole system, the whole host, more performant. And you should also know that for channels, if you go with message passing, it adds some extra data, extra space. So it could be significant if you have a lot of messages, a lot of small messages. And of course, implementation is unsafe. Yeah, we can do it without it. Actually, how to measure it? We can go with perf again. We can ask for perf stats. And we can ask about this particular thread, how often it logs. So we have contentions, we have context switches, we have branch misses, cache misses. It's the most significant part. So you can check when you develop a program how logs behave in your particular case. So we can analyze it with perf stats. And if you need to go with more detailed approach, you can choose BPF. It's a Turing complete program running in kernel. So it's only on safe Rust running in kernel, but also BPF. So it's a simple case of BPF. How to understand when do we log is to make some hooks from the user space program, and we just run our program, and we check when each thread acquires the mutex and when it, when the process is forked, so we make a new thread pool, and when it exits, yeah? So for BPF, you can check a lot of different things, how to do it. It's really complex, but it's really helpful. Don't forget about it. And for logs, this is the case how to track the log usage. So for example, if you run only 3 threads, we get uncontented mutex. So this one is ours, yeah? And if you go with 5 threads and 100 logs, we get much worse case. So perf log is your good friend for analyzing log contention. It's actually a hard choice how to choose a good abstraction level. So first of all, go with a really, really high level iterate abstraction with Rayon. If you need communication between the parts of your program, choose one from STD if you have only one receiver, or choose a channel between different receivers. And you can also tinker with doing it on bounded channel, really, or you can go with back pressure. And if you need omnidirectional access, so it's a normal data structure, a normal queue, you can choose the crossbeam one. And async channels, no luck. You can go with Flume or Tokyo, because it's totally different thing. We don't even mention Tokyo here or async. And for looking data structures, old one, ERC, mutex, blah, blah, blah. And actually, we discussed a high-level parallelism. It's about Pareto tasks, yeah? But let's understand what can we do more. It's about how to utilize the hardware. The low-level data parallelism is about how do we ask our system to do the task parallelism inside the hardware. So we don't actually care. We don't use any atomics. We don't use any logs. So it's enabled in hardware in truly parallel manner. So for this, we have CMD, single instruction, multiple data. So it means we can execute the same operation on multiple data points. The operations are pretty much limited. It's about normal operators, add, sum, reduce, and the rest, yeah? And they're really, really highly process dependent. First of all, you probably don't need to write this code, because after vectorization is pretty good, yeah? The Rust compiler is based on LLVM. So you can utilize all the optimizations from LLVM when you just generated the code. So this part is probably handled really, really good by the LLVM. But you need to compile it in release, yeah? I think it's pretty obvious, and you must help compiler to do it. Because if you just slap a bunch of vectors, it wouldn't work, yeah? The simpler is better. You need to make slices only. You need to put preconditions, like this array contains at least this amount of char elements, and yeah, you should not reuse the variables. So all these cases, they should help you to do this, to do after vectorization. And how can you check it? You just run cargo awesome on your Rust code on a actual program, and you check if you have any instructions related to XMM or AMM. If it does not mean it's performed. Yeah, it's only about it contains some data. So in low level, how does it work? So we have stable API. Stable doesn't mean unsafe. Stable means it's assigned to the Rust library. And we have a bunch of intrinsics. So we have a type called M256, and it relates to the register. Yeah. So the registers. Here I draw it a smaller register. It's not YMM. It's a little smaller because I don't want to write 8 of them. One register can contain multiple data points. So in modern architectures, you can have even up to 60 elements in one. So you ask hardware to do operation in truly parallel manner. Yeah. So you have this. You load the data to the register. Then you call the add function. It translates to this assembly, so you can spot it in assembly code. If you're lucky to see this, it means your attempt works. Yeah, and then we get it back, and we get a large loop around this, so we can make it in chunks. So actually, it's even this. It's an abstraction because this doesn't relate to the specific register, because hardware and the good compiler will translate it to operations only for 2 registers. So it adds in place, yeah? Because yeah, why don't do it, yeah? And all this reloading is done by hardware, yeah? So we don't care about it. We just put a bunch of types and load store operators, yeah? So what's the state? In this year, we have stable support for all the major architectures. For Intel, we have up to AVX2. It means we can fit 8 floats or 8 integers, 32-bit integers to the register. AVX, more performant AVX is not available because it wasn't available in hardware, actually. The stable neon support for ARM is here for 64, and for old one, I don't know how you use the old ARMs, but yeah, it's nightly. So it means you're pretty much good with SIM support. And if you need to go in more abstract way, you can use the portable SIM. So the portable SIM is great, but it is included as a STD CMD. So it means we have a pretty good chance to have it in the standard library soon, yeah. And currently it works best with advanced stuff from Rust library like chunking, and it's much more ergonomic, but unfortunately it's nightly only. So yeah, the primitive operation is to use a type, a normal type, CMD, over the specific type you want to wrap, and it specifies the lane count. More about lanes later. And then you can go with really good Rust-specific converters, like from slice, to slice. You can even pick whatever you want from your array, so quite good, yeah? And the best part, you don't need to write all the intrinsics, yeah? You write the safe code, not unsafe, and you use a normal operation like a normal people, yeah? You can multiply, add, and yeah, that's much better. And if you build it for Haswell, for an architecture with AWX, we can see in assembly that we actually use the registers, yeah? IMM, it means we have AWX, yeah? AVX. And we just fire a few instructions generated automatically by portable SIMD, yeah? It's really good. And if we run it for Nihalim, for really old CPU, probably I have it in my drawer somewhere. How can it work? Because it's if you just run it, it doesn't have a wide register. It's only about 128 bits, right? So how could it work? Actually, if you check the assembly, we'll see that it uses normal registers, yeah? And it's a magic. Portable SIMD actually writes our program to support only specific instruction set. It's really good, yeah? And the CMD lane we've seen in this part, it's really virtual, yeah. So it doesn't relate to actual CMD width, yeah. We usually specify it for 32, so it doesn't matter. It's much more abstract way, and we can also write a program with normal iterators, zips, reducers, and yeah, portable SIMD is the choice. Next, if you want to actually specify for which architecture do we generate code for, we use target arch, yeah? And we say, okay, we'll compile this program for feature AVX and for specific CPU. So usually you want to use this because a specific CPU is quite difficult to specify because you can run on AMD or whatever you want. And yeah, as a native, it's harmful, don't use it. So can you spot the difference between the two of them? They're quite similar. Actually, the first one is compiled only if we have the feature enabled in our compiler settings. And the second one generates the code for AVX. So it means the second function can contain the code specific to this particular architecture. So if you run it on old processor, we'll have a crash. We don't want to have a crash. We don't even have unsafe in our programs. So for this, we need to go with feature detection. It's really common practice for portable binaries. So we can have helpers. We ask the compiler, not the compiler, okay. We ask the system we're executing on, do you support this particular feature, like AVX? And we can target our code for multiple architectures in the same time. And we can have a multiplexer. It's a safe function. So we compile this chunk only for Intel, and we route to different implementations. Yeah. So for AVX, for native code, and we only have a specific function for specific architecture generating the code for this instruction set. Yeah. So it's unsafe code wrapped in safe wrapper. So you can go wrong, probably. Still not blazing fast, so we implemented all the advices I specified, so we need to understand the caches closer to hardware. So if we need to load a byte from memory, it isn't loaded like a 1 byte. We load the whole cache line to the particular core. So it means all the rest of accesses for subsequent chunks of memory will be much faster. So what could go wrong? If you have a structure, packet in memory, in a way that different CPUs have it in one cache line, we'll have a problem, because it will be insanely fast. Because each time we modify the cache line, it will be trashed, it will be invalidated for other CPU. So each time you modify the head, you add some data to the structure, you'll get invalidation. So it's really bad. How Rust helps us? It helps us with a really good thing called cache padded. No one safe here, we're lucky. So it allows us to add a padding depending on the architecture. So for example, for Intel we have, it's a bit overkill because usually it's 64 bytes only, but yeah, it's for future. And we add some padding, and also it allows us to align the beginning of each data field in the structure to the specific cache line, yeah? So it helps us a lot. If you're writing or utilizing concurrent code, please be sure your data fields are padded. And extra techniques. Don't forget about LTO. So LTO is linker time optimization. So since we are using the LVM compiler, we can utilize the optimization in the linker stage. So enable it. It's off by default. For slower build, but a little faster binary, you can deparallelize compilation. So you can set code gen units to 1. Could help, yeah? And for a really performant code, use inline, because it's not inlined by default, right? And choose your arithmetics. Because if you choose unchecked as or saturated as, you can have some benefits in really performance-sensitive code. By the way, the checks are on in non-release builds, so it means in debug you have a different behavior. So always check in both debug and release. And finally, you could probably go with a really high-level abstraction like Apache Arrow. Yeah. So it utilizes zero copy. So you don't need to move all the bytes between file on the disk from the network, and you can utilize vectorized execution. So we have a lot of really handy frameworks. So for example, for data processing, for database engines, for example, Apache.flow, for InfluxDB, we use Apache Arrow a lot. And then let's tackle a bit what the GPU state. So what's the GPU? It's a thing you could buy before the AI boom, and you could run some games on it. Unfortunately, I didn't run games on it because I did research for parallel GPU programming, so how to run actual scientific code on it. So it's massively parallel. We have a lot of different execution units sitting on this GPU, so we can have a stream of data. And we have a lot of these CUDA cores trying to execute the same operation on the stream of the data. Yeah, so it's highly parallel. It has really thousands of processors. So first of all, we have specialized code running on chip, on the actual CUDA core, and we have code communicating with the GPU. So how does it like? First of all, it's really complicated. We have a ton of different binary formats. First of all, CUDA kernels are written in C++ with heavy language extensions, and then LLVM compiler tries to translate it to intermediate representation, like mir in Rust, yeah. And NVIDIA specific one is NVVM, and then it translates it to the binary. PTX is like a binary code in your binary sitting on a machine, yeah. And then PTX is shipped to the GPU over the network or over the host connection, and then the host runtime coordinates, because GPU is a coprocessor. So you ask, okay, run this workload, I will wait for it. And you can do it asynchronously, so you don't need to wait until the completion. So what's the state of the ecosystem? First of all, if you go with simple Rust GPU, you will find it's a graphics library. It's not bad, but if you don't need to write some games, it's not for you. Then you can go with NVPTX. NVPTX is the implementation given from LLVM to us, how to provide actually the PTX code. I don't think it goes anywhere because it's inexperimental, and we have a much better approach, the Rust CUDA. I was lucky enough to spot that in January it was rebooted, and it's really exciting because it allows us to write kernels in Rust instead of C++, and it allows us to have an interconnection between host and GPU written in Rust as well. So yeah, I'm really excited about this. So what's inside? First of all, it's a native Rust backend to emit LLVM. So it actually wraps LLVM compiler, and we need to have it as a part of the Rust C, because currently it's off kernel. And then it's a host toolkit. Usually we use C++ runtime API in heavy CUDA SDK, but Rust CUDA goes a little lower, and it tries to use the driver API to handle all the communications between host and GPU. And finally, the GPU part is a bit tricky because it doesn't support a lot of different language constructs. So for example, imagine if you have Rust code able to only add or divide things. Oh, yeah, it wouldn't be so fun, yeah? So we definitely need to reach feature parity with LLVM. But yeah, if you're going to check some experiments with CUDA code, you can go with GPU Rust. So to conclude, first of all, start with a really high-level parallel abstractions. Best of all is a task-based parallelism, not instruction-level parallelism. So choose rayons with iterators over the pure lambdas. Choose channels if you want to exchange messages between different tasks, so you don't share the state, especially the mutable state. Choose the portable SIMD, because it's the cleanest way how to utilize, actually for free, the headway parallelism. So if you have arithmetic operations, if you have, for example, computations, you'll definitely benefit from using CMD. And on the then delve into the really low-level optimization, because Rust is a system language. It allows us to have all the hardware primitives in our fingertips, so we can use all the features from the processor, all the features from the system. So we can use any syscall you want, yeah. And then learn how to customize your tooling, how to target a specific architecture. So you can tailor the whole binary of your program to be really hardware independent. Yeah, so you can have the same binary running on ARM with really high performance on Intel. So yeah, that's really easy. And always measure. Yeah, don't trust yourself. Measure with benchmarks, measure with profilers, get some flame graphs, and compare. And finally, yeah, as I said, tailor implementations for different platforms. So yeah, what's to read? A lot of different things to read about. Even the C++, if you spotted it here, it's really good. And then you got a lot of stuff about atomics, logs, about Rayon. And if you're really excited about how to develop hardware, you can check a small book from Intel. But yeah, it's really, nowadays you can just ask Intel, okay, please can you send me this manual? ARM guys, please tell me, can we have your books for free as well? So I hope we can. So yeah, thank you for attention. You can reach out for questions, inquiries, and yeah, thank you. Questions?
Thank you. Any questions? Thanks for the amazing lightning talk. About the GPU-specific libraries, the downside of CUDA is it's vendor-specific, as you know. Are there also very good libraries if you want to... I know they're behind in implementation, but that might not always be the case. So if you want to use, for instance, AMD hardware, or maybe even AI accelerators, are there other similar libraries available to...
What's the name? Could you recall?
Sorry?
What's the name?
My name? Sorry?
The name of the library.
Oh, no, I'm asking you. Do you know of any? Do you know of any?
I hope you got some insights about the new library. Unfortunately, I'm not aware about this. So usually people just go with C++ code in GPUs, in kernels, and they just write some glue code in the host. So it's executed only in host system, yeah? So almost every case will be covered with C++ code running on the actual GPU. But you can utilize how to connect it to your program with Rust code. So unfortunately, we have not so much libraries available. So Rust code probably the easiest one to use.
Hello. Thank you for the very interesting talk. I only found about Rayon yesterday. Fairly new to Rust. I'm certainly going to use that. That's very exciting. Because I'm currently working in quantum computation and quantum computing, first thing came to my mind, are you planning to implement any APIs for quantum computer calls, like Q, for example, from NVIDIA? That's the question. Sorry.
It's a tricky one. So actually, right now you don't have a lot of choices how to do it. So you need to generate some code, some really specific code for GPU. You need to write some glue from the host system. So everything needs to be supported from the compiler. And the Rust compiler is not yet providing all the stuff. So we are currently waiting for support from the ecosystem, from the tooling. And yeah, we cannot just go and write our crate to do it. So that's the situation.
Q library started doing that. They provide emulation layer for the quantum computation.
It runs on host, yeah? It could be a good idea. So I really hope the Rust code authors won't implement the same stuff from NVIDIA, because it's a community effort. It's not backed by the NVIDIA. So if NVIDIA provides it as a stable or beta, it's a really good sign. So yeah, let's try it.
I had a question about the inline attribute, because I was thinking about it as being a trade-off between frequently called functions and ones that are better left uninline. So when should you use inline, I guess?
If you have some code which is on the hot path, so you move all the parameters between stack frames, you will benefit from using inline always. It's per function, yeah? So you need to isolate your function. By the way, if you place inline always, your analysis with perf or with flame graphs will be a bit different, because if you omit the frame pointers, so if you don't have actual function, it will be impossible to understand where is it. So it's hard to spot this one. So I suggest to analyze the flame graphs to see the most called function, and then it could be a good candidate to be inlined. I hope I answered the question.
Hi, thank you very much for a great talk. I have a question about automated parallelization. This is like entire field as well. In parallel computing, do you know any solution specific for Rust? So you simply provide code which is like purely synchronous, let's say huge computation on a big array, and you can generate the parallel program out of it. Is there any solution for that?
Generate from what? From the another program?
Yes, yeah, like, well, there is entire field in C and C++, and then quite well-working libraries around like converting synchronous programs into parallel programs. I'm curious if something like that.
In C++, it's quite popular. So, for example, the C++ programmers usually apply it after vectorization by placing some random instructions like pragmas and commands inside the code. So it says, okay, this loop is going to be parallelized. Please unroll it multiple times, yeah? And it usually goes to the hints to the compiler. That's how a lot of different tools work. And if you want to actually generate code, I don't know, actually, will the Rust developers love it, the generated code, because we are not happy with macros. Probably it would be a mess to read, but who knows? Probably it could be a good idea to check. But I highly doubt that generated code could be really high performant. It's only my opinion.
Okay, thank you very much for your presentation. I have a question about the configuration depending on the target architecture. I can understand the configuration is powerful for to achieve it, but I guess it's a little difficult to maintain it. For example, testing and benchmarking and catching up the state-of-the-art CPU architecture. Do you have any ideas to make it easy for the maintenance?
How to benchmark it, actually, yeah? Usually you have a fixed parameter, like the architecture. So you're running on a specific machine, right? So in this case, the profiling goes to getting some performance counters from perf using flame graphs, and that's probably all. If you move to another architecture, you have this fixed parameter as well, so you need to only check this architecture. So how to make sure that the whole program, independent of the specific code for this specific architecture, it's hard choice. Probably it's a good idea to use Criterion and Hyperfine just to profile in the end-to-end manner. So check this.
Hi, did you have a view on profile-guided optimization, PGO? Does it help with automatically inlining functions? Profile-guided optimization, PGO?
Yeah, good one. So the profile-guided optimization, profile-guided optimization, PGO actually, yeah? It's a good approach that helps a lot of people in C++, and it uses really heavy. So it means you can have a program collecting the traces for the first run, then you collect all the data, and then you feed it to the compiler for the second pass to generate optimized code. So unfortunately, I hadn't used it with Rust. Probably it's a good idea if you have a workload, for example, for, I don't know, for beta stage of your system. You can collect the data with negligible cost, yeah? And then you make a really good optimized binary for the production. So I think you can integrate it into your CI pipeline or testing benchmarks. And yeah, you can definitely benefit from this. I don't remember actually how to do PGO on Rust. I would appreciate if someone could share.
Evgenii will still be around to answer any questions, but we now need to go to break. We've got a half-an-hour break. Thanks again. Evgenii.
Yeah.